I would like to thank you very much for the invitation. I'm sorry I cannot be here. It's mostly due to the strike. Coming was not a problem. Coming back to France was seems to be much difficult than ever. So the point of my talk, we try to highlight some pros and cons we had from a perspective of a lab, to transfer technology from labs to industry, and I will have a very specific focus for the future of aircraft manufacturing. So first, I would like to stress that there have been a lot of collaboration between various laboratory and Airbus. So by no means I am representing the point of view of Airbus or CNRS at large. For instance, some of my colleagues have been finishing a very interesting H2020 European project called Humanoid, and with very nice results. And what we are doing here is a slightly different focus. Based on these following problems, right now, if you look at the website of KUKA Aerospace, the current technical robot that you can find are these 250 kilograms end effector, done specifically for drilling and screwing. And to manipulate them, you need a 2 tons robots here, and to move the robots around the aircraft, you need civil engineering investment, and the cost of this kind of robot is really big, really high. And when you cannot sell the aircraft, you end up with a lot of investment on yourself, and it's very costly. So the point is to try to have a kind of partial automation on this kind of system, where you can redeploy, replan, and be more versatile, knowing that you have to be in this 3D task called dirty, dull, and dangerous task, and this is quite difficult. As you may have heard from Boeing, for instance, that they have been trying to go toward a full, a very highly automatized process, and they were unfortunately not successful. So the point is, if you look at real environment like this one, you can see that having this kind of robots inside the aircraft is quite difficult. You have stairs, you have a lot of small areas, and despite this high level of technicity, right now at Airbus, when they drill 125 million of holes per year, 75% are done manual. So the main idea would be to have some kind of robots which will be versatile. So I would say that the dream-like robot will be to have a humanoid robot being able to do something like humans. But right now this is, I think, out of reach. But it's a very nice to drive academia, develop new algorithms that have after a direct impact on industry, and I will try to highlight this kind of indirect impact of humanoid technology. So in one hand, you have human robots like the Humanoid, which are safe. You can interact with it. It's very compliant, but not very powerful. And the other spectrum of this kind of robot, you have the Atlas robot using hydraulic embedded power, but for which it's extremely difficult to get a certification to be close by, because the pressure involved by the robot is very powerful, and at the same time the robustness and the repeatability is still an open question. So what we have been trying to do is to propose an intermediate robot called Talos. So we specified it, we made a tender together, so based on the targeted application with Airbus, and it was actually won by PAL Robotics, that you may probably know because it's a very important actor in ROS. So to go toward this humanoid robot for the factory of the future, the main goal is to have safety and power. And for us, safety and power will be achieved through planning and control. So to do that, what we do, again, we use humanoid robot as a scientific flagship. And the point is for us is to, through pragmatic proof of concept, try to transfer this technology in other robots, such as Tiago, here, in where we simulate a model of an aircraft, where we try to put silent, and using exactly the same software that were developed for the humanoid robot. So in terms of history, that was again based on reactive motion planning. So in 2013, with Airbus, we have proved that in real time, we were able to go generate in real time motion for the robot when only specifying holes on the 3D mock-up of the pylon of an engine, of a flying wing here. Then we have shown that we were able in real time to generate stable motion while the robot is climbing stairs. In 2015, we have shown again in real time that we're able to compensate for the forces generated by a robot, humanoid robot holding a fire hose. And in 2016, with the HRP2, we were able to climb stairs in multi-contact. And one of the main problems with this kind of robot is that we were at the limit of the current that we were able to deliver. And actually holding the ramp was one way of decreasing the needed current that is needed to climb stairs. And based on this is where we specified the new robot called Piran. So Piran is just, I would say, the first name of what is now a brand, the Talos robot. There are now 5 in various laboratories. And last year we get Tiago, that we also use for teaching purposes. And this year we integrate this new laboratory with Airbus, where we try to apply the same algorithm from Piran to Tiago. So in terms of vision, the kind of variability we would like to be able to achieve is a variability induced by the customer. So for instance, here you have some needs from the Singapore Airlines client who asked to have a specific flat inside the aircraft. And this impacts the aircraft. You need structural changes. And this means that if you are building a specific aircraft for a customer, you need to replan and change the behavior of the robot. There's also the fact that there is a lot of human inside the chain, so they may come up with their very, very nice ability, but there are also some variability in the realization of the task, and you'll be able to adapt to that. And variability in the delivery, for instance, when suppliers, and there are plenty of suppliers in Airbus, are, for example, late, you need to reschedule some of the tasks, and again, that would be nice to have the robot to adapt to. Finally, the 4 and 5 problems we would like to try to handle is a collaboration with human, and last but not the least, certification. So, in order to address this, what we try to do is to have a flexibility and composability, to be not trapped in a very specific software architecture or to be trapped in the architecture provided by a supplier. Again, something I think that has been proven very helpful in computer science, like for example for APH with IBM versus Microsoft, is to have all the source code be v2. So everything we are generating in this lab and by Airbus and LAAS are completely open source. And so I talk about the composability in terms of software, which I think is inherent with ROS. We are also trying to achieve mechanical modularity. So we have a special relationship with Spal Robotics, where, for instance, the arm, what we like to be able is to exchange the arm of the Tiago with the arm of the humanoid robot. So the main idea was coming from maybe you remember the Shaft robot that was bought by Google, and which show that you can have very powerful and flexible robots even with electric-based system, and this is what currently driving us. I would like to tell you that we are as good as this guy in this video, but we are still far to achieve this yet. But we think that you don't need the hydraulics to make useful, repeatable, and interesting, versatile robot, and able to do to handle strong tools like driller or screwer, weight something like 2 or 3 kilograms. So here, for example, you have an HRP tool being able to, in real time, build a 3D map of his environment and do planning. So it's still an kind of flat environment, but you'll see at some point they are working on gravel. And again, reactivity is paramount here. You are controlling 32 motors with gravels and environment, and you are still stable. So for us, scientific flagship is very helpful in terms of new idea. And in order to go towards this direction, we have 4 work package. The most important one is real-time planning. The second one is to do torque control. The third one is simultaneous localization and map building. And the fourth work package is balance. So in terms of challenge, what we would like to do is to be able to climb stairs with this robot, but handling real stairs in, for example, in Airbus aircraft factory. And the height of the staircase is very high, it's 20 centimeters. So if you are handling tools, you probably need multi-contact in order to stay stable. And we would like also to become strong and good. So in terms of ROS, I think to achieve this goal, there is some very key component that we have been seeing to achieve this is ROS control. And I really believe that at least something like ROS control is a must-have, and I will try to make the case for that. And something also we have seen it with our partner in Airbus, that they were very strong on the non-real-time capability of the middleware in ROS-I, specifically for the field buses, in order to control the intermediate robot. So we were really looking forward to ROS-II, but still some preliminary result. And here I gave 2 recent survey on the capability of ROS-II. I think there is still some work in terms of, for example, jitter, in terms of bus field. A comparison done by the team of Aleixno on the OPC UR versus ROS, an open source implementation of ROS-II. OPC UR was better. And a recent paper on the IEEE transaction of automation show that the PCL Open, or the implementation of PCL Open, was better than, again, the current DDS implementation that we have in ROS-II. But what I really like, despite this, is that if we need, it will be, I think, very nice to have ROS-II wrapper around these 2 protocols in order to cope with this current problem. So I think we are going into the right direction to cope with these very important problems for industry. Now, in terms of ROS control, I would like to give a very short introduction for people who may not know ROS control. It provides an abstraction of the hardware interface, which is very nice for people like us who are providing controllers, in the fact that it's completely hiding the real hardware, and it gives us a standard way to actually propose controller. And this is how we can use exactly the same software for Talos and Tiago. It's because all the software of PAL Robotics are coming with this hardware interface, which is hiding IMU encoders, force sensor, currents, motors, and where we can provide our whole body controllers. So in terms of nice exchange between academia and industry, PAL Robotics, their first implementation of ROS control, they are providing independent controllers, for example, to control it independently the torso, the arm, and the head of Thiago. So everything is completely decoupled. The problem is that as soon as you do fast motion, then you end up with a dynamical problem, a balance problem that has to be taken care of. And you need to have a whole body control. And PAL Robotics, actually, they look at our implementation of the whole body controller we have been doing 10 years ago. And it was for them the first basis of their own whole body controller. And now they are selling a product that you can buy if you need to do this kind of whole body control. And again, something I found very important, at least for academia and for industry, is the composability, in the sense that this is not something you have to use. This is an option. And if you want to, you can put your own control into the system. And because for us, it will be so much costly to do our own controller that at the end, you use a control proposed by a company such as PAL Robotics, because you are gaining time by not re-implementing your own stuff. And as a customer, have the freedom to switch from one controller to the other. So I think this is very nice, both for the customer, for the academia, and for the integrators. So for our own architecture, what we have been developing is that this RC SOT controller. So where we have a graph a bit like Simulink, where we can handle different kind of plots. And we interact with ROS and Python to actually change this graph when needed. And thanks to ROS control, we can switch between gazebo and the real robot in a seamless manner. And I wish that would be possible, for example, with Webbots, the very nice simulator that was presented just before. So in terms of real-time, what is very interesting for us is that all the real-time is handled by the robot hardware. So you can have, for example, Wine River VNX system, RTV. This is what we have on Talos. And our controller is just held by this overall interface. And we pay great care of having all these small components being extremely efficient to run at 1 kilohertz inside the system. And they can be handled through ROS by a Python interpreter, which is running in a non-real-time thread in parallel to this system. So in terms of path planning, we have developed HPP, which is a reboot of Kineo for the people who may know this path planner, which has been recently bought by Siemens, and which was a spin-off of our laboratory. So the stack of tasks, which is our control system, is now connected with HPP through a new project called Agimus, which is currently a planning task. So here you have the Talos robot, which just has one task, is to put this box upside down. And the only thing which is provided to the overall structure is the fact that the robot is handling object with this end effector. You have 4 possible handle at the level of the object, and the robot will find by itself the sequence of controller it has to perform in order to switch the box upside down. Everything is embedded inside the robot, and takes in total 2 minutes to happen. So of course here you can see it's not optimized yet. So we are working in the optimization of this system. But the nice thing is that there is not so much effort from the user in order to solve this kind of very difficult problem. Okay, so in terms of low-level core control, again, thanks to ROS control, we have been able to switch between the PAL torque control software layer and our own implementation. So this is something we are porting right now. So we did develop a torque control for HRP2, where you can see that the person is able to interact directly with the robot. And you can, for example, take the leg, and the robot will automatically put the force on the other part. And PAL Robotics shows something very nice, similar to that, even more efficient on their own robot. And it was ported on our robot this year. So I would say that right now, having an industrial, a robot that you can buy and on top of which you can do torque control is feasible. And even so, there is a lot of research to do. We hope that it's going to be reproduced in other labs in the world. So again, so it was something we've been trying to do is to do differential dynamic programming in one motor here, where basically we're able to go up to 30 kilograms on this robot. What we have shown is that using differential dynamic programming, you can put 34 kilograms on this robot, and he will automatically not follow the task, making sure that he's not going over the torque limits here on the system. The motor are not burning. The limits here are the harmonic drive. In terms of perception, we are just collaborating with our colleague in the frame of a European project called MEMO, and here you have a rendering of our colleague from Oxford University, Maurice Brown, more precisely, and which has already integrated into ROS some very nice packages, allowing to have 1 centimeter of precision in very big industrial plants, and which was for us up now very challenging, how to be precise to do planning in this very large environment, industrial environment. And finally, in terms of balance, again, using this ROS control architecture, we have been able to replace the whole infrastructure of PAL Robotics, implement our own system, our own solution. So again, on this fact, I think this is a very nice thing that has been that we have been able to achieve thanks to ROS. And as a takeaway message, I will say yes, ROS control is nice. It has its defects. But I think right now there is a ROS-2 implementation which will allow to have compatibility in terms of hardware, which will allow us to overcome this limitation of ROS control. And what I believe right now is that having ROS allows us to have a tighter integration between lab and industry, given the fact that you have this BST2 license, that you have this possibility. And I will push forward into the direction of ROS2 and real-time capabilities. And this will end my presentation. And I thank you very much for your attention.
Thank you, Olivier. It was very good. Nice presentation. Question. How big is the gap between OPC UA and ROS2, and how fast do you think it can be closed?
That's a good question. To be honest, so I can give you more the reference of the paper. So far for me, it was never problems because I was mostly focusing on ROS control. The main point of my colleagues was mostly to do bus-to-bus connection between two robots, one doing telepresence and the other making the interaction with the human, where it was important. And what they were showing that they have significant less jitter. But again, that was 1.5 year past. So I think now the newest implementation of DDS are probably better. However, during the ROSCON conference, I'm not sure I've seen people making this kind of a comparison as the one of the two papers that I mentioned previously, with a lot of different kind of use case.
Olivier, it's kind of difficult, I think, for discussing via Skype.
I thank you very much, Olivier.
And I'm very sorry I couldn't come. That would have been my pleasure. I hope to come back another year and meet people in person.
See you next year.
Thank you.
See you.